I'm trying to position machine learning here on this little diagram, and you can think about knowledge-driven systems such as expert systems, and you can think about data-driven approaches, statistics. And machine learning is also data-driven like statistics. The big difference is that we kind of give up on interpretability. We don't try to understand everything, and we move more towards a black box. So black box fanatics came up with neural networks 20 years ago, and I'm not going to go that far. I will stay within statistical machine learning, kind of reasonable theory, but not try to understand everything. And I think in the second talk, my colleague Srinivas will probably add a little bit more knowledge about computational linguistics. So I guess probably this morning you are more into statistic pattern recognition. I will take you to machine learning, scaling up things, and then Srinivas will add more linguistic knowledge to get you into computational linguistics. So the title of my talk is not so important, but I just want to stress one aspect of machine learning I will talk in particular, which is kernel versus feature engineering. Basically, what I'm going to try to describe are classifiers that generalize and scale well and that are good for natural language application. There is a huge range of approach, and I'm going to focus on simple learning blocks and very important, reliable algorithms. What I mean is that when you run the algorithm, you have a reasonable guarantee that this algorithm is going to converge and that it's going to generalize on test data. And deployable algorithm is that both the training time and the runtime are manageable. And the key challenge, obviously, is going to beat the curse of dimensionality, which lead us to good generalization on test data. We will also have problem with structure, and we want to scale learning to really very large corpora. I really mean millions, even billions of training examples. Now, the outline will start with a statistical learning theory. This is really going to be the only theory in the whole talk. And then the kernel engineering part of the talk is going to be the kind of fun, maybe not so useful, but you'll see part of the talk. The meat of the talk will be about linear classifiers relying on feature engineering, and that's going to be the one you want to remember if you want to understand what Srinivas will talk about. And I will also try to introduce you to good software to use if you are interested in pursuing machine learning for any type of application. Now, at this stage, I'd like to know who is more in. Are you more kind of natural language processing or speech processing here in your background, or open? So speech, who consider himself as a speech person? I mean, speech recognition and, okay, and natural language? It's kind of 50-50. Well, apologies to the speech people. I will not address the problem in deep detail. What I mean is that I will only consider machine learning to categorical data in my examples, even though it would be very easy to generalize this to numerical data. For some strange reasons, the main machine learning technique used in speech in speech and natural language, HMM, is not considered as part of the machine learning field. Don't ask me why. I mean, HMM people publish at ICASP, not at Machine Learning Conference. Maybe it's a solved problem. So let's start with our key building block, binary classifiers. So we have some training data, and X will always be the input, Y will be the output. Usually, input is a fixed size vector, and then we'll move to structure. And the output is, at this stage, a binary class. Either -1 or +1. And the following generalization of the output are possible. We can move to Y as a probability estimator. We can apply regression. We can do multi-category classification, so then Y belongs to a discrete set from 1 to L. we can use output codes, or Y can be some kind of a structure, a tree, a sequence. And that's the, and I will cover some of those cases beyond binary classifiers. So now let's start, let's go very quickly. Well, stop me if there is anything you want me to clarify, but this is just going to be a 10,000 feet overview of statistical learning theory. We are looking for techniques to predict the generalization error and for methods to minimize this error. And the model is that we observe data generated by an unknown distribution. The only thing we know is that it's IID, I mean, independent, identically distributed. And basically, the analysis of the learning problem amounts to what function can the machine implement and what is the capacity of this class of function. So empirical risk minimization is really the key concept that enabled to formalize machine learning. Basically, so here as a classifier, we want to learn the association between X and Y through a function f, and we want to minimize the expected risk on a test set drawn from this P of X and Y, which is unknown. So this is what I called my expected risk, this formula. Do we have a pointer somewhere? Oh, maybe.
There may be one.
You know what? It would be nicer, but usually I may have one. Gosh. Let's just no. I normally have one with my key ring, but I took the wrong set of key.
I can be back in a couple of minutes.
That's okay. I mean, I have some. So this is the expected risk. Obviously, I mean, it's an ideal risk. We cannot really compute that. And we are going to approximate this. We need an induction principle, basically, here. And so instead, what we have access to is the empirical risk, which is the measure of the loss function over the training data 1 to m. Okay? So now we know, according to the law of large numbers, that when m converges to infinity, this empirical risk will converge to the expected risk. But how fast? So, and what guarantees? What is really important here is that this convergence has to be uniform over every possible function that we can learn. Otherwise, I mean, there is always the risk that we are going to end up with this function that, that doesn't converge uniformly. So basically, you have a great training error and a lousy test error. So the bounds to guarantee this convergence were established by Vladimir Vapnik. You have probably heard that name. And they typically establish that with a probability of 1 minus delta, the expected risk is bounded by the empirical risk plus 1 over the number of examples at some power alpha, multiplied by a constant which is a measure of the representation power of the function class f. And for instance, the famous Vapnik-Chernovenkis or VC dimension. So how can we use that in practice? The bounds that are actually being published are hugely over-pessimistic. I mean, you need a massive number of examples to guarantee convergence, but you still get the idea. And the main idea is that those bounds are dimension-free, which means that they do not depend on the dimension of the sample space. And this is what we want to beat the curse of dimensionality. And while they cannot be used for accurate prediction, they suggest how to constrain your class of function, for instance, by keeping the Vapnik, the VCD as small as possible in order to beat the curse of dimensionality. And the first success story of the use for the use of those bounds were the support vector machines and kernel methods. So let's look at support vector machines, which have now been generalized under the name large margin classifiers. So basically, we are here looking at linear classifier of the type sign of the dot product of a weight vector between the input vector plus b. So this is the kind of your typical linear classifier, and then we take a hard decision. And we are going to, and for those classifier, Vapnik established that the bound is of the form, okay? I guess I'm all set, right?
Yeah, you're all set now, but yeah, you got my lectures.
They established that yes, it works. Yours great. That those bounds are of the form order of the square of the diameter of the data divided by the margin. So let's understand those concepts. Basically, you imagine this is your data. The red examples are the positive example. The blue examples are, say, the negative examples. And you want to draw a separating hyperplane. And here you start with a very simple case. Data is separable. So that's one possible separation. Obviously, it's not a really good one because if you just did a little bit of jitter of those examples, you would have errors. What you want to do is to look for the plane which gives you the maximum separation margin between the positive and the negative examples. And it's kind of intuitive that this one is going to be a good separation because even if you jitter the plane or you jitter the separation plane or the examples, you are not going to add errors. And if you train your W to correspond to that separation plan, that's where you get this bound, which is the ratio of this the diameter of the data d divided by the margin m. Up. If the data is not separable, then you will have to use a soft margin, which I will use later, describe later. So now, how do you find the maximum margin separation? And basically, what we want to do here is to find a weight vector that is going to maximize the margin m. Here, I think there is a notation problem, with the constraint that this weight vector stays 1, and that every example is on the proper side of the margin. So when y is +1, it's above the margin, and when y is -1, it's below -m. And the reason why you want to constrain the weight norm to be 1 is because otherwise you could always get this by growing W to infinity. So now, and now I'm all set. Basically, what you do is you do a Laplace optimization, and you basically have the choice of parameters. You can either optimize for the primal coefficients, which is directly the weight vector W, or you can also look for in the dual space for the combination of training vectors, because basically it's trivial to show that the optimal separating hyperplane corresponds to a weight which is a weighted combination of the training vectors. And when those weights are non-zero, they are called support vectors. The interest of this dual computation is that all computation will be represented as inner dot products. So f of x is a dot product between w and x, and can be decomposed as sum over all the training vectors of alpha I, the dot product of this training vector, with the vector for which you want to measure the score. Now that you have understood, this is a great concept to understand, is that you only have to bother about measuring dot product between vectors in your input space with this method. Nothing else. You don't even have to look at your features. Oh, I just wanted to mention in passing what the margin would be if we had outliers, which mean that the data was not separable. In this case, you can imagine that each of those outliers is attached to a spring, which causes a linear cost of 1 minus y per f of x. Now we can, so So far, okay, so do you have any questions so far? I just here have described a very simple technique to train linear classifiers with optimal generalization according to the VC principle. Now, how do we use this classifier? The question is, how do we define a good feature set in which we want to operate this classifier? And obviously, one constraint is that the space has to be large enough to separate examples, at least reasonably. I mean, you can use a soft margin classifiers, but there's a cost attached to it. Now, in my talk, there will be two approaches. One is what I call the kernel engineering approach, where various kernel can create an implicit feature space of huge dimension. So again, this is the concept of embedding your data in an Euclidean space. And imagine that a Hilbert space is an Euclidean space that can be of infinite dimension. The price for this flexibility will be the computation cost, as I will show you. And the feature engineering approach, which is usually favored by computational linguists because you have more control over it, is that the expert defines a large enough feature set. And the good side of it is that you will see that we can use any type of classifier, not only SVMs.
In the kernel engineering approach, you still need an expert to define the kernel and its parameters.
Kernel engineer, yeah, the expert will focus on the kernel instead of the features. It's a little bit of a more abstract exercise. So some abstract-oriented people prefer kernel engineering. But yes, you need that. And it's, in a way, more fun, too. So now, one thing we have seen so far is that we have only looked at flat input, I mean, in an Euclidean space. And at one point, we'll have to deal with structure inputs. So just to give you a foretaste of what's going to happen, we want to go to sequences, tree, graph, something. And basically, there are three approaches to deal with structure. One is inside the classifier, and where the kernel induces a linear feature space from the structure. And this is what I'm going to describe in this lecture in quite a lot of detail. The second way to do it is outside the classifier, where the structure is handled by some graphical model which is going to call the classifier. And this is basically what Srinivas will use in his lecture to actually use classification. So that's a more practical approach. And another very interesting way to do it is outside but optimized jointly. In this case, both the graphical model and the classifier minimize a single error, for instance, with structural linear classifiers. I will not get into details here. If anybody has seen Ben Taskar's presentation last year, I mean, he's really the expert, and I would never be able to match his knowledge on this. And so I will point you to his slide if you're really interested in details. So now, so let's go into kernel engineering, my specialty. And we are going to try to make kernels and kernels for structured data. And in particular, we're going to look at string and weighted automata. That's to please Jason. So now, what's the point of a kernel? Basically, the idea is that your data lives in some small dimension input space where, not so small, but not so, where you cannot really separate it. And what you want is to project your data into a much larger space when a linear separation is possible. And you have some preprocessing function that is going to be responsible for this projection. The problem is that the linear classification in this very large dimension space is expensive, and the preprocessing can be expensive too. So we want to do all of them together. Now let me show you. Let me show you this from an example. We are going to. No, this is not. This is the wrong side. So, so here remember that the only thing we are using in the optimization of an SVM are the dot product between the examples. So basically, what we can do is to replace the dot. We can replace the dot product between the transform of x and the transform of z by a function over x and z, and we can use that function directly in our optimization process. The benefits is that in this case, there is no need to define and compute phi explicitly. And as I'm going to show you, k may be much more efficient to compute than the dot product. We also gain a great deal of flexibility. K can be chosen arbitrarily so long as the existence of phi is guaranteed, even if we don't know its actual form. And there is a very simple condition, which is that k is a positive definite symmetric function. And that's, so what is a PDS? So take your training data and define the kernel matrix Kij as being the kernel between all the training examples. All we are asking is for k to be symmetric with positive eigenvalues. This property must hold for every possible training data set that you can imagine. So for all m and for all set of size m. So basically, the positive definite condition writes like this. But it basically requires positive eigenvalues for any training set you can pick after computing this matrix. It's a condition that has been verified for a lot of functions. I'm going to show you one, which is a polynomial kernel. So imagine a linear classifier over all pairs of input features. And so you have about d square feature. And a dot product in the Hilbert space here would cost you about O of d square operation. Now you can use the kernel trick to make this much faster. So here, the transform phi of x is going to transform a vector into the set of the product of every possible pair. And when you compute phi of x multiplied by phi of z, you get this product that factorizes this way and just turns out to be the dot product squared. And this is our kernel. After we do that, we only need O of d operation because we only need to compute the dot product in the input space of dimension d, even though we are actually operating a linear classifier in a space of dimension d square. That's the magic. And this can generalize to any degree polynomial. And by changing the degree of the polynomial, you have a control over the number of features in your Hilbert space and control over the capacity of your class of classifier over your VC dimension. And you can choose this d using, for instance, cross-validation. Now, let me show you a success story for kernels. I mean, that was probably the first success story. It was about optical character recognition 12 years ago. So this is really a very well-known reference data set. I mean, everybody in machine learning knows about MNIST. There are 60,000 training examples. The images are 28 by 28, so 784 pixels. You can see how noisy those characters are. They were used, I think they are used on postal envelopes. And it was found that the best performance for this data was obtained with a 9-degree polynomial kernel. So basically, with this kernel, at reasonable computational cost, you have a feature space of 3 multiplied by 10 at the power of 20 pixel ninople as features. And SVMs beat all other methods for this. For instance, you can see that a linear classifier will give you 8% error, while the 9-degree polynomial SVM gives you 0.6% error. Yes?
How does this compare to, for example, an RBF kernel? How long to find that?
Okay, on this data, I can tell you that provided that the examples are normalized on the unit sphere, there is an asymptotic equivalence between polynomial and RBF kernels.
For what degree, as the polynomial degree goes to infinity?
The polynomial degree, there is a correspondence between the polynomial degree and the gamma or the R of the RBF kernel. It's very easy to do this on the back of the envelope. And I did verify that. In practice, for categorical data, like in natural language, and this is why I mostly discuss polynomial, I prefer polynomial kernels. RBFs are a little bit better for numerical data, I would say. Now, in fact, this is a very general way to describe the RBF. Is basically we'll get to RBF through this way. I found a very interesting approach is to make kernel from distances, because a kernel is a measure of similarity. It's a dot product, but a distance I think is more intuitive for the kernel engineers. So we want to imagine what. I like distance. I mean, they're easy to visualize. Let's say it that way. And we have tools to turn distance into kernel, provided that they are symmetric, positive, negative, which is a condition which is very similar to the positive definite. And and I thought at one point that every distance, as soon as you add the triangle inequality, you would get that condition. And I spent something like 1 or 2 years trying to prove that the edit distance was symmetric, negative definite. Unfortunately, it's probably one of the few distance that is not suitable for a kernel, and this is a big problem for us. But that's just a little side thought. Well, in this case, the key property is that exponential minus t, the distance is positive definite for all t larger than 0. So we have made a kernel out of a distance, and a Gaussian kernel is you just made it out of the Euclidean distance. Now that's the standard one from the Euclidean distance, but is it the best one? Very often not. Let's take a case where your input vector represents a distribution. And the ideal distance you could imagine on that will be the KL divergence. It's not a distance, but usually it can be approximated by either the Hellinger distance, which is the Euclidean distance between the square root of the feature, or the L1 distance. And both those distances are negative definite symmetric, and you can also make kernels. And I found in practice that for many applications, the Laplacian kernel, which corresponds to the L1 distance, is much more interesting than the Gaussian kernel, which corresponds to the L2 distance. Especially, yes.
Why you say that divergence, curvature divergence is not a distance, but I'm a symmetrical one?
It's not a distance, it's a divergence.
It's not symmetrical one.
Huh?
A symmetrical divergence, curvature divergence is a distance.
Oh, yes, but is it, yes, you are correct. And when I did that work, I didn't look at it. Now we have to check whether it's negative definite symmetric. Yeah, I should look at that, yes.
Because a lot of application is based on that.
But to be honest, I found that the L1 or Hellinger do a pretty good job already. I mean, and they are very simple.
We already tested in our field, in
yes.
vector recognition.
Yeah.
The kernel divergence, the symmetric kernel divergence,
yes.
Kernel, and also the Bhattacharya kernel, and it gives the same result.
Yes. Oh, great, excellent. But my favorite is the Bhattacharya Hellinger kernel, because it's just you just take the square root of the feature and then you can use your standard Gaussian kernel. Okay, now here is a distance kernel success stories. You may be familiar with the famous WebKB data sets, which are home pages gathered from university computer science departments, and you want to classify them as student or faculty. And the feature space is just going to be bag of words. So basically you put all the words from a web page in a bag, and the distribution is P of W is the probability to take word W out of the bag. I mean, that's the idea of the bag of word. It's a histogram, a word histogram. And it seems, and actually, I got the best result using the Bhattacharya-Hellinger kernel here. I should try yours, but that was done a long time ago, so I'm not sure I even have the code left. Now, those kernels are fun to play with, and you can do a lot of stuff, and I will show you more, but let me warn you about the drawback is the runtime implementation of a kernel. So here, when you play around with kernels, you have to be in the dual, which means that the way your classifier is represented is by those Lagrange multiplier, 1 per training examples. Now, let's suppose you have a new example X. To classify it with the dot product of Wx is going to be the sum of alpha I kernel of xi x. And the complexity is the number of support vector multiplied by the time to compute the kernel. And very often, the number of support vector can be a good fraction of the entire number of training examples. So this is really a killer. Now, if the kernel was linear, which means that the kernel is simply the dot product, then we go back to our good old dot product, and the complexity is just the number of non-zero feature in X. So here, I mean, this is the price to pay for kernel, and you have to keep this in mind. But let's forget about it for the time being and try to make kernel even more complex kernels. So far, we have only looked at flat, fixed-size input vectors. And we are going to see what we can do on structure objects. For instance, we have a lot of them here in spoken dialogue classification. We have graphs, for instance, the lattice output by the ASR system. In text categorization, we have strings. In parsing, we have trees. In part of speech tagging, we have string and trees. So now, the traditional method, which I will describe later, is feature extraction. But what about using kernels as a measure of similarity between some of those objects? Let's see what we can do. So here, what I want to do is I have this structure object, and I want the structure kernel to project them into an implicit, to embed them into an implicit Hilbert space where I can do my classification. There has been a lot of literature on that. And it's interesting to categorize it into model-driven approaches where the knowledge about the object is encoded in models or relationship. And here we have the Fisher kernels, which is built from which is very often built from a generative model of graphical model. And we have diffusion kernels where the local relationships are encoded as graph. Closest to natural language processing, we have syntax-driven kernels, where the objects are generated by syntactic rules, trees, variable length sequences, or distribution of variable length sequences. An example of tree kernel is the following. So if you are lazy, you can do a subtree tree kernel. So basically here, the object you want to classify is a tree. You are going to encode the tree by a string traversing it, and then you can use a string kernel, which I will describe later. And if you are very thorough, you can do a subset kernel tree, which is a recursive construction, and with application to re-ranking of parsing trees and shallow semantic parsing. Now, this tree kernel required the definition. The first tree kernel is similar to a string kernel, which is probably the most studied kernel in natural language processing. So let's see what type of feature can be extracted from a string. Bag of word feature sets, which have been very successful in text categorization, but also grammar fragments or n-grams, which have been useful in spoken dialogue classification, or variable length n-gram in computational biology. So all this suggests that we want to extract subsequences from strings, and we want to base our kernel on matching subsequences with gap and mismatches, and even with distribution over those. So here is the way a string kernel works. So basically, the string kernel is going to try to measure the similarity between cat and bat. Let's first imagine we don't have access to the kernel trick and we want to do an explicit extraction of all subsequences. And the time as a function of the string of the string length, assuming that you can go to subsequences of that length, is exponential. So cat in cat will have A, C, T, CA, CT, AT. So those are subsequences with gaps that we can get from cat. Here are subsequences up to length 2 that we can get from bat. And the kernel is going to count the number of matches. So looks simple here, but it's exponential in time. So a string kernel will be based on a recursive computation that starts from subsequences of length 1, 2, 3, 4. So here this is the recursive computation from t minus 2, t minus 1, and t. And one can show that in this case the time is linear. So here what the kernel trick gives you is going from an exponential to a linear time as a function of the length of the subsequences. So string kernels have been published since 1999, and especially in computational biology. And one thing we worked a lot at AT&T were lattice kernels for spoken language understanding, where the lattice is the weighted alternative of sequences represented as a finite state automata, which encodes the output of a speech recognizer. So here is an example of a lattice. This is the output of a recognizer. As you can see, you have a very large number of paths of alternate sequences. So matching all that would be extremely expensive. And in this weighted automata, weights are used to rank alternative sequences. Now, I think I will go very quickly here. It's kind of presenting my own work. And I just, we built a kernel on that. I want to have time for the rest for later. And I want to show you the benefit of such a kernel. So this is the only experiments I will present. Srinivas will be in charge of presenting the other experiments that we did. We have a customer, so this is a spoken language classification problem. It was started at AT&T under the name How May I Help You in the late 90s, and I think it was the first spoken language classification system. A customer calls a service and speaks naturally, and the speech recognition output is this acyclic weighted automata. The goal is to route the call or send it to a dialog managers, and the categories are call types or named entities such as billing, services, calling plans. We studied 3 deployed customer care applications for healthcare and telecommunication industries with between 60 and 100 categories. And the data was about 10 to 35,000 training utterances. And here you can see what's the payoff of using the lattice kernel. So we start from a bag of word feature from the one best sentence, kind of the standard approach. And the error was about 29%. That was used with a support vector machine already. Then we used word bigrams. We got to about 24%. Trigrams doesn't improve much. We're still at 24%. So this is kind of the best you can do using the one best. Now, if you use the lattice instead of the one best with a lattice kernel, we get down to 23%. And we can obviously fold this, if we can the good thing about kernel is that you can combine one kernel on top of one another. So here we were using the lattice kernel alone, or rational kernel. And here we are going to combine the lattice, aka rational kernel, with the polynomial kernel to gain another percent and reach 22%. But as I told you, there is a price to pay in runtime performance. This is much slower. This is very slow compared to this. And this gives you another idea of how badly a kernel scale. So this is on this task, you have the training time as a function of the set size, and you can see that the training time for a second order polynomial SVM is exactly parallel to a O of n square reference. On the other hand, some algorithms that have been that only train the classifier linearly, like linear SVM, and some other that I will describe later, like AdaBoost or maximum entropy, have a much better scaling behavior, and their training time only grows linearly with the set size. Again, the price to pay. So basically, here we have seen the kernel approach, which is the implicit transform. A lot of fun to play with. However, if you want to scale data, you probably will have to do some pre-processing and do an explicit transform, and then do the direct inner product. And now I'm going to describe this scenario in the second part of my talk. So the structure kernel. So the structure kernel we have seen, they provide a framework to understand what type of kernel we can build. They provide an efficient and generic implementation. They avoid computing features whose number in theory grows exponentially. However, in practice, we'll find out that because the data is sparse, very often the number of non-zero features may be surprisingly small. So now we may find cases where we can prefer a combination of uncrafted preprocessing and linear classifiers. And this is typically because first, computational linguists have already spent a lot of time in crafting those features, so why not use them? And we'll get a much faster runtime implementation. So now here's so this is the second part. I'm moving from complex to simple, and from small to big. I mean, if you understand it. So I'm looking at classification problem in natural language application that really become very large. I mean, with a large number of examples, large number of possible features. However, a small number of non-zero features, and the examples abound in spoken language understanding, text categorization, tagging, machine translation. In machine translation, we have examples where we have more than 100,000 classes and 1 million examples, like in bytext classification. So the general way to, let me generalize linear classifiers in what I call margin-based linear classifiers. They do include SVM, but they do include a lot of other interesting classifiers. So we have just a linear classifier with trainable weight. And the only hypothesis we make is that the loss function is a combination of two terms. One is the sample loss, which is computed from the sample margin, which is how far we are from the separation, which is just the label multiplied by f of x. And the regularization term, which measures the complexity of the model and encourages a simple model. When I talk about regularization, for me, there is only two choices, L1 and L2. Some people also mention L0, but good luck for the optimization of L0. But L0 is very interesting. But I will just stay around for.
Can you say what L0 is?
Huh?
Can you say what L0
L0 is just counting the number of features, and L1 is the Euclidean norm, and L1 is the L1 norm, and L2 is the Euclidean norm of the weight vector.
Counting the number of features, you mean the number of features with non-zero?
Yeah, it's counting the number of non-zero features. Yes.
So to keep that small means most of your features should be
So now let's try to understand why L1 is called sparser than L2. So basically here, try to imagine that we want to minimize the norm of the weight, which is very often what you do, under the constraint that at one example is classified is on the proper side of the margin. So basically here, this is the weight space, and this is a linear constraint. This is a linear constraint of the weight, which corresponds to this plane, and this means that our weight parameters. You know what? I think I got the wrong. Is this wrong? Is the proper? I may have to I may want to. I think I was actually trying here to maximize the weight. Okay, because here I want to find in this half weight space. Okay, what is? Okay, so this is okay. So this is the space where the weight is below that constraint, and this is not actually the minimization of the weight. This is actually okay. Here's the trick. Now I want my weight to be on that space, but I want my weight to be on the unit sphere. So this is the Euclidean unit sphere, and this is the Laplacian unit sphere. And you can see that the Laplacian unit sphere is going to hit that plane where only one of the weight is non-zero, while the Euclidean unit sphere will hit the plane anywhere, as there is no incentive for having a zero weight. I'm sorry, this is a very old slide. I haven't been through it for a long time.
There's something else about this slide that may
Yeah.
be confusing people.
Yeah.
That P should be a subscript.
Absolutely,
far up.
absolutely. But it's also P equal constant under the yeah.
Right, but it's not multiplication by a
Yes,
scalar.
absolutely.
But,
So, well, after I've defined this combination of loss plus regularization, I can immediately reinterpret SVM in this context. In the SVM, basically the sample loss corresponds to the hinge loss in a simple way. You just want the sample margin to be if it's larger than 1, you are fine, and if it's lower than 1, you are going to incur a loss. And the regularizer is the Euclidean norm of the weight. You could also use the L1 norm in the case of the SVM, but then the kernel trick becomes impossible. So it's tricky. Now, as we are more comfortable looking at our features, and we can also look at feature-based learning algorithms. And here, I mean, those algorithms have been very popular in computational linguistics, as they really try to do the optimization in the feature space. Like a good example is AdaBoost, where features are explicitly interpreted as weak classifiers, and AdaBoost incrementally refines a weighted combination of weak classifiers. And the importance of examples that remain erroneous is adaptively boosted, hence AdaBoost. Another interesting example is maximum entropy, where features are interpreted as constraints. And we look for the distribution over a training example with maximum entropy satisfying this constraint. And we'll find that by that this will correspond to some maximum likelihood problem. So let's look at boosting, because it's a nice intuitive algorithm, still very attractive for NLP problems. So here, let's go back to my call classification problems. So this is an example of call that we want to classify as pay bill. I want to make a payment. I want to pay my bill. I would like to pay the bill. I would like to pay my mother's long distance bill. And obviously, here you can see that there's some kind of obvious rule of thumbs, like the detection of pay or bill, that are easy to find. So can we formalize this as a training algorithm? And this is exactly what boosting does. It's a method for converting rules of thumb or weak classifier into accurate prediction rules. Now, so that's the idea. Now, boosting is a whole family of algorithm where, given the training examples, the same training examples that we had for SVMs, you are going to iterate over those training examples, and you are going to update a distribution over these examples by finding a weak hypothesis which is going to minimize the error on this distribution. And you update this distribution initially is uniform and slowly will focus on errors, and then you will specialize more and more your features in correcting the last remaining errors. Sounds like the highway to overfitting. Surprisingly enough, no. AdaBoost generalizes pretty well. And this is the most famous member of the family, AdaBoost, and with the following weight update factor. So those are kind of the mathematics behind it. And AdaBoost can be shown to be a margin classifier, well, sort of a margin classifier. So basically, it actually corresponds to the following: exponential sampling loss. We can also use a logistic loss. There is no explicit regularization, but there are some generalization error bounds which are based on the L1 margin. Another very interesting classifier is maximum entropy. I guess you should be familiar with it. I mean, reasonably familiar.
You might take a show of hands. I'm not sure how many people.
Yeah, are you familiar with maximum entropy? About half of them. Okay.
Maybe fewer than half. I mean, we have a number of undergraduates here. We have people from a linguistics background.
So I'll just go very quickly through it. So suppose, so here we want to model the conditional distribution probability of output given the input. So for the in our call classification problem, let's take this. So the feature f of x are words in the sentence x. And now intuitively, a key interesting measure is the frequency a word f corresponds to a label y, which is going to be measured with this joint probability. So here I'm just measuring the empirical probability on the training data. Now, suppose we want to build a model P parameterized by W. So this probability is computed through a model parameterized with W to produce the label. Then I'm going and then this is the frequency estimated by the model, and a good model should get it right. So basically, that the empirical frequency is equal to the estimated frequency, and this is the constraint that you are going to use. You want to find the simplest model satisfying this constraint. And it's easy to show that it corresponds to an exponential classifier minimizing the conditional likelihood. So basically, the PW of x given y is basically going to be exponential of W x with the normalization constant. Now, maximum entropy is also a margin classifier, so I just go very quickly here through the binary case so that you see the similarity with AdaBoost and SVM. The loss function is going to be the logarithm of PW of x given y, and which corresponds to this very simple margin-based sample loss. And for the regularizer, what is nice with the maxent is that we do have the choice between L1 and L2. I am a big fan of L1. But most people do use L2. Okay, so I've covered three classifiers. My favorite, SVM, AdaBoost, maxent. Now I am going to move to a second part, another type of presentation using PowerPoint. Okay. And I want to I want to come to how we are going to actually to give you a feeling of the optimization algorithm that we actually use for those classifiers in practice to make them really fast, considering they're linear. So here you see here that in the first talk, we have seen kernel SVMs where the parameters that we wanted to estimate were along the dimension of the training vectors in the dual space and with one non-zero multiplier per support vector. So alpha 1, alpha 2, alpha 6 here. And in the second part of the talk, I discussed linear classifier where you have one weight per features, W1, W6. So here you see you have a critical choice in how your model is represented. And this critical, and now I'm going to give you a general perspective of how, depending on this, this is going to drive the choice of your algorithm in a pretty generic way. So,
Quick question with that.
Yeah.
The number of alphas is less than the number of x's, right?
yes, the number of I'm just using all the alphas here, but you are mostly interested. The only alphas you are going to bother about are the non-zero alphas. Yes.
Okay.
I said yes.
The w's has the same number of w's as features.
Not necessarily. You can your weight vector W hopefully is going to be sparse too, and you certainly want your weight vector W to be sparse when you have millions of features. So both those vectors are sparse, or are expected to be sparse.
Right. But the dimensionality of the vector.
So basically that's a representation trick. The dimensionality of those vectors, this vector, if you represent it flat, will be the number of training example, and here the number of features. I never do that. I always have index value lists, and I only represented the non-zero features in either dimension for everything. And in fact, we'll go through a few graphs to understand that. So, how much time? Oh, you have 30 minutes, right? So the optimization algorithms so if we're in a dual space, I haven't really got into the gory detail of SVM optimization. And I will focus on the perceptron, which is pretty much the same idea, but a little bit simpler. But basically, in the dual algorithm, you have an algorithm called sequential minimum optimization for SVMs. In the primal algorithm, I will show you an interesting way to optimize AdaBoost or L1 regularized maxent using a greedy coordinate descent algorithm. And something that works both in the dual and primal space is stochastic gradient descent, which is really the one algorithm you want to use whenever possible because it's so incredibly fast. The sequential optimization in the dual space, let's take a simplified example. So I have an example I with input xi and target yi. So this is a training example, and I want to store, I'm going to store for each training example the score, and I will update it later. And here the sum is over the support vector alpha k xk. Then I look for the worst violator, and given this violator, I am going to do an exact analytical step to modify my model F. Remember that my model F is encoded by the alphas, by adding the worst violators to support vectors with Lagrange multiplier alpha I, so that the violator is classified with the proper margin. So I'm just going to get alpha I so that this is larger than 1. And there is a very so this is what I would call a kernel perceptron algorithm, and there's a very similar algorithm for SVMs called sequential minimal optimization, but you need to add at least 2 examples to balance some constraints. But it's the gist of the idea, a greedy algorithm, and I'll describe it in this figure. So basically, you start with your data. Initially, you have a blank model. You look your first worst violator is the training vector x6. x6 you add with a -1 Lagrange multiplier because it's a negative example. Then you have a positive example x1 with a positive Lagrange multiplier, and your model is done. So basically, what you can see that you iterate. You iterate over examples in a greedy way with an exact analytical step. Now, interestingly enough, the algorithm that we use for AdaBoost or L1 regularized maxent is the exact transpose of that, where you are going to iterate over features in a greedy way until you converge. And now let's move to stochastic gradient descent. A stochastic gradient descent can minimize any form of margin loss plus regularizer. Preferably, the regularizer has to be L2. So this is the general case, and with the loss in the case of the SVM. And the weights are just updated with a trivial gradient descent procedure. So a gradient step size multiplied by the gradient itself, which contains both the weight a weight decay and a term specific to the new example you add. Now the magic of gradient descent is the choice of the step size and the weight decay. And so typically the step size has to be 1 over lambda t to obtain convergence. Now this algorithm we're going to see the results are excellent. It's only last year that we realized that it was so good. Why? Because you have two trade-offs in gradient descent. You need to find a schedule in the step size so that it converges to the optimum. So t here is the number of iterations. So if you have if you add 1, for instance, in the case of the perceptron, then you get a lot of oscillation. If you add 1 over t squared, then as sum over 1 over t squared is a finite value, it would bring the learning rate to 0 too quickly. So that's the first thing you must remember with gradient descent. There is an optimum decay in your learning rate to avoid either oscillation or learning to 0 too quickly. The second trade-off is you need to properly combine the schedule in the step size and the weight decay. And in the case of L2 classifiers such as SVM, this problem was only solved last year. I can give you some reference for it. But the so
by
yeah.
weight decay, you mean the strength of the L1 power?
Yeah, sorry.
L1 or L2?
What did I say here? Properly comment the step size and oh yes,
I'm not sure you just
it's not the weight decay. It's the regularizer parameter. You are perfectly right. Now now basically the difference between the greedy algorithm presented before and stochastic gradient is that it goes through the data in a linear way, so it can be used in an online way. So here you can imagine the gradient descent just going through your training data. It just go iteratively, linearly, and it benefits from the fact that your data is stored, the way your data is stored to be extremely fast. And here are some examples. So I'm compare here. Those are various. Natural language problems with between 500,000 and 1 million examples and between 50,000 and 300,000 features. Those examples are very sparse. So this is the type of training time required in seconds. Some of them take days, using a very well optimized SVM library. With this library, this is actually libSVM. And basically, you need days of training. And this is my own software where I kind of really spent years totally optimizing SVM on sparse data. And I thought I did the best I got the best possible training speed for SVM. And when last year I saw the Bo2 getting this speed, I was kind of, I lost, I was a little bit upset. So basically, compared to older SVM algorithm, gradient you can move from days to seconds sometimes. It can be spectacular. Obviously, this only applies to non-kernel methods, linear classifiers. Now, I have only described binary classification so far. Let's go multi-class. Large Manual classifiers are by essence binary, so we will have to do. And we have many combinations of binary classifiers possible. The most commonly used is one versus other, which separate example belong to one class from all others. But there is also 1 versus 1 where each classifier is trained to separate a pair of classes, which is very fast, which is much faster to train because you have smaller training sets. You also have error correcting output codes and hierarchical approaches which have been recently studied. However, the most common is 1 versus other. Now, the problem with methods based on recombination of binary classifier is each classifier solves a different optimization problem, and there is no guarantee for global optimality. So now a global optimization procedure is possible but expensive. I mean, you definitely need to you need to multiply your memory and your time requirement at least by C, number of classes, sometimes by C squares. So now let's look at some more specific multi-class algorithm. Most of them are going to define a multi-class sample margin where you compute the difference between the target class output and the best wrong output. And this will have to be larger than 1, for instance. As I said, in this case, the global optimization is costly without really, I've never found strong improvements from that. So you can do that with AdaBoost and you can do that with SVMs. You can also do this in a probabilistic framework. Maximum entropy offers many ways to define distribution over multiple classes. The price you pay with maximum entropy is the partition function Z. As the number of class grows, becomes very expensive to compute. And in fact, there is no free lunch. It's about the same price as. So multi-class is always expensive because of that. And now, I'm going very fast now because I don't want to miss my conclusion. It's kind of natural to move from multi-class to structure outputs. So far, what we have looked at were discrete enumerations, but can our output follow a structure? For instance, every possible parse tree. So here we have an example where our classifiers, instead of producing a class, produces a tree from an input sentence. Now, the number of classes is the number of possible trees, can grow exponentially. Fortunately, you can factorize the model using compositionality. And here, this is where I will not get into details. It's very important to note that here, the goal is very different from tree kernel. Here, your tree is the output. In a tree kernel, the tree would be the input, and you would still have some kind of discrete class at the output. It's one important thing to note is if you want to do sequence classification, so you have there is a big difference between the structured output method and the static classifier method. So if I was just using a flat static classifier for each token.
Now by sequence classification, you mean the sequence is the output?
Yeah, the sequence is the output, yes.
In the previous slide, the sequence or the tree was the input.
In the previous slide, I was talking about trees. But structure can be either trees or sequence, so I just wanted to cover all the cases. So here the simplest thing to do is to train a flat classifier for each token, and then we will recover the sequence using some dynamic programming. The drawback is that you need to do it when you train the system. You need to do a token level supervision, and the training labels must be aligned at the token level. Now, the alternative is to do sequence level supervision, and that's what structure output classifier do. Now, to give you an intuition of why this is going to be very costly, is that the training algorithm will be more optimum, but it will have a train time to explore every possible alignment. One can see that if you have looked at CRF, for instance, this exploration of every possible alignment is done in the partition function, which is so expensive to compute. So that's the price you have to pay. Now, okay, so I have 15 minutes for the conclusion, which is exactly what I wanted. And this is where I really want to be interrupted. So I'm going to go very slowly through all those questions, and if you have your own question, please come in. The first one, which so far I skipped, because basically for some strange Basically, it's probably obvious to you, but this lecture is purely focused on discriminative model, which is to predict a class Y given X, and where we only try to look at the separation between classes. We don't try to model the entire data. But obviously, there is a whole class of learning architecture called generative models, where you model the entire distribution P of X and Y. And the problem with those approaches is that you have to rely on a probabilistic model that represents reality well to give good performance. Basically, they are trained with maximum likelihood, and maximum likelihood will minimize your classification error if the true distribution is among the distribution represented by your model. This has been highly successful in speech recognition with hidden Markov models. I found on average that generative models are not so competitive for natural language processing tasks. And Srinivas will give you some comparison between discriminant classifiers and HMMs on the problem. I mean, I don't know if you have observed, you've played around with that. Now, the second question, which is the one I have talked a lot during my talk, is kernel versus feature engineering. And this is probably where I've built the most expertise so you have two situations. Let's say I have a problem. The first case, which is I don't have a good feature set. Which is very, computational linguists always have a good feature set, unfortunately, but I assume I don't have one. And so basically here, the idea is you start on a small subset and you play around with kernels. And those kernel, and then you do all the kernel engineering stuff, play around with polynomial kernels, imagine distance, put the exponential and all this stuff. And this is going to give you some ideas for good features. For instance, if a 3-degree polynomial kernel works very well, that kind of suggests that triplets or trigrams of words are probably some good features. So this is what I should use as features. In the case of rational kernels, which are the lattice kernels, we found that they work pretty well. But as a matter of fact, the corresponding feature space corresponds to n-gram probabilities. And actually, so it's suggested to use n-gram, that the best possible feature were n-gram probabilities. Now, after you have played around with kernel and got some ideas for features, then you get rid of the kernels and you expand to a linear classifier on a large data set. Now, even if you have a good feature set, kernel can give you more structure, but honestly, I don't think that kernels are the most efficient way to deal with structure because they are so expensive. And an absolute fundamental problem is also the choice of L1 versus L2 regularization in your regularization term. I mean, we would all love to, L1 is very attractive. The benefits may be the benefits are obviously quantitative. You have much fewer parameters, thus smaller models and faster runtime. And here, sometimes I'm talking about orders of magnitude. So it really makes a difference if your model is 10 times smaller and run 10 times faster. Now, and also qualitative is that L1 explicitly asks you to choose between correlated features. And very often in NLP problem, this is a good thing. You really want to, you have this underlying idea that there's only that this should amount to a single feature, especially if you have already crafted your features. However, this is not always desirable. You have to be careful about that. The price to pay with L1 regularization is that first, fewer models are suitable for L1 regularization. You cannot use kernels, for instance. And also algorithms such as stochastic gradient descent, I should not say do not work, but are not very efficient. The reason is that the stochastic gradient descent, even when it knows it's L1 and that most of the weights should be 0 at the end, during most of the processing, it will create those small values that it will have to bring to zero later. So in fact, in the case of L1 regularization, I found that algorithms that do feature descent, the algorithm that optimize greedily one feature after another, are much more efficient, because you are just going to look for the non-zero feature you are interested in. Now, another big question, which I have not discussed much, is a flat versus structure classifier. So as we saw in the sequence level, this amounts to a choice of supervision. Shall I do my supervision at the token, the frame level, and then I would do sequence alignment as post-processing, or shall I do it at the sequence level? Well, in theory, okay, now let me say two things. Is that in theory, structural approaches are more optimal. But there is this kind of no free lunch rule, is that every structural approach that I know, whether it's structure support vector machine or CRF, scale in O of the number of labels square. So and this is probably the main reason why in the problem Srinivas is going to describe to you, he will always use a frame level supervision approach, not a structure approach, because he will show you models where the number of labels is between 5,000 and 300,000. You cannot square that. The complexity is too large. Short. Okay. Yes. Another point is that recent benchmarks show little difference on problems such as chunking or tagging. I think we at AT&T, we never managed to get a sequence level training to significantly outperform a frame level training. But I think Manning also had some similar results, and I've heard a lot of those results.
There's a paper by Manning and Todunova on
Yes.
part of speech tagging that I think you're talking
Yes,
about.
yes.
Where so yesterday we were taking care in reconstructing weather sequence, like speech tag sequence, to look at the context of a particular day. So when you reconstruct the weather of a particular day, you're interested in the days before and after. So Manning and Todunova said, well, suppose we just look at the amount of ice cream you ate yesterday, today, and tomorrow. And try to predict today's weather from that. And so you're just doing this local classification instead of this complicated alpha beta computation that we did. For part of speech tagging, you do just as well, maybe even a little better. So you look at the current word and the surrounding words, and based on that window, try to make a prediction. Yeah, and there are other tricks that people can do here. So you could, for example, say. You could do what's called classifier stacking. So you have every word predicted, its most likely tag, and then you do another prediction where you look at the tags from the first round of prediction on this word and on surrounding words, and maybe you do this for a couple of levels, where each time you do it, you have access to the predictions you made the previous time for this word and previous words, and this is sort of still a relatively local way of making these predictions. And I guess you're saying you're getting the same results across tasks.
Pretty much just, well, across the few tasks we have looked at. But this is, and I don't understand why, and this is also one of the reasons why I didn't insist on structure classifier in my lecture, is that I feel there is something we don't do proper, there is something wrong with them, because they should be better, and I don't know why. I don't know what we are doing wrong. Maybe also that in the frame level supervision, we benefit from added knowledge that we give, because we give the frame level labels from which, I mean, this label.
No, I mean, I think
this labeling contains some knowledge. I mean,
there's an advantage and a disadvantage to switching. So the disadvantage is that you really are only looking locally. Yeah. So the fact that it was hot weather 10 days ago is not going to influence you at all, because you're only looking at the surrounding days. But the advantage is that you're looking at more than just whether it's hot or cold on the surrounding days. You're looking at the actual number of ice creams. And there's more information there, because there's only 2 tags, hot and cold, but there's 3 levels of ice cream. So if the actual number is relevant, you're paying attention to it. So the model actually has more parameters.
So now
you don't get this fun dynamic programming forward backward thing, which is really quite beautiful and gets to look at the entire data set, but you're looking more closely at what you do look at.
No, it's okay. No, go ahead. So this is really something that is fascinating. A new development in machine learning started about 2 years ago when Joshua Bengio, who is in fact the start to talk to me at NIPS and say it's time to dekernelize machine learning, get rid of kernels and go back to good old neural networks. So basically, the idea here is that machine learning has been going through phases. Neural networks were old-fashioned up till 95, and then with the advent of support vector machine maximum entropy, all the approaches we have been working on are linear when it comes to learning. I mean, basically what you are learning are parameters of a linear system. They require added non-learnable human knowledge to work through the kernel, the feature, or the structure engineering. But the basic is linear, and thanks to it's to be linear is a good thing, because then your optimization problem is convex and guaranteed to converge. But it's also a bad thing, meaning that there is kind of no way you can really learn hidden concepts. So there is a small group of machine learning scientists, mostly led by Hinton, Jan LeCun, Joshua Bengio. We have been arguing for decades for deep networks such as multi-layer perceptron and Boltzmann machines, where they can learn complex nonlinear mappings. They are cognitively more attractive because they can learn hidden concepts. However, learning is not convex, and convergence is tricky. And until recently, it was really considered as a black art. So basically, only machine learning expert could do it, and a computational linguist could not get its black box off the shelf, run it, and it would converge. I mean, you would have all those things to tweak around. Fortunately, recent advances have made the training of those machines much more stable. And they have got some strikingly good results on natural language processing problems, where they in particular show that they took, for instance, one of the most complex problems, which is semantic role labeling, where the state of the art was obtained with an enormous SVM, taking every possible features on the face of the planet, but that had been very carefully engineered, obtained from a parser and thing. And they could just, by taking the string of word input, match that performance, because the multi-layer perceptron was able to learn all the hidden concept necessary. So this is a work by Weston and Colbert from NEC. So I think this is a fascinating and very promising approaches. I can't advertise it well. When I asked them for the tools are not ready yet. So talking about tools, here is what you can use right now. And if you're familiar, if you have any question, please go. So I always start with Weka. I think that's this is always, Weka is a wonderful little piece of code. It's very flexible. It implements pretty much every single classifier you can think of. You can combine them. You can boost SVMs if you want. It has great visualization. The only problem is it's Java, and it kind of crashes after 10,000 examples. But otherwise, it's great. Then if you want to, and it doesn't do very scalable. It doesn't do structured. Now, if you want to scale up to SVMs, and in the case of SVM-like, structure SVM, libSVM and SVM-like are two very reliable pieces of code. Torsten Joachims has on his website has some new versions for structure SVMs, I mean, which are constantly updated. If you're interested in applying maximum entropy or conditional random field specifically to natural language problems, the tool of choice would be Mallet. If you want to build your own solution, especially a deep network or a multi-layer perceptron, I would recommend Torch 5. It's in fact by Colbert and Weston, the authors of this new work I mentioned. You can find, if you like MATLAB, there are many small apps for MATLAB on this website. The software I use personally is Weka, libSVM for benchmark, and I have also my own software. But unfortunately, it's not public, but I would say it's kind of pretty similar to libSVM with special extension to Maxent. Okay, that's about it. I mean, if you have any question.
What did they train on for that semantic overlay? Or
Excuse me?
what did they train on, Weston and Colbert?
Are you familiar with that problem?
A little bit.
They train on the prop bank. And yeah, they did the Wall Street Journal, and so something interesting is that so basically they managed to not use any tagging or parsing features and match the state of the art. They use also some unsupervised data, so they train the hidden layer to do more than learn the prop bank, but they do co-training on other problems so that the hidden layer can do kind of complex linguistic inference that goes beyond the prop bank. I think they have they have probably a paper at ICML. Any other questions about software? I mean, very trivial questions. I mean, I'm here for that. I mean, if you have a practical problem and you want to know what software to use, something like that. This is pretty much my job at AT&T. People come to me and say, I have this machine learning problem. What should I do?
So suppose somebody has some crazy new function that they want to optimize. Should they download Leonard's stochastic gradient descent code?
Oh, it's a fantastic code, yes. I should have mentioned it, but it's kind of a toy code. It's a toy problem. It's a very good code, yeah.
Yeah, I mean, it's not specifically for machine learning, but if you had some new method, then you might want to do it.
Well, this stochastic gradient descent is specific for machine learning, this code.
Well, it's a general function optimizer, right?
No, it's just, I mean, the code, the code for, it's a code for SVM stochastic. It's basically a code for stochastic gradient descent in SVM and Maxent. And basically, if I go back to this slide, it's this code is about, I think it's about 3 lines of code. It just implements those two functions. And the only thing there is only one variable you can change. You can change that loss between the hinge loss and the log loss. But it's really 3 lines of code.
I see. So if you wanted to do structured classification or something, this code would not do it.
No, but he has a generalization of the code to CRF. That's the only structure classification he has. But it's for CRF, you still there is no free lunch there. I mean, this code you still need to compute this bloody partition function, which is in L square of the number of labels. Okay, well, thanks a lot.